For like 2,000 years, we thought of electricity and magnetism as two totally separate things. One was that crackle you get from static electricity, and the other was the weird, silent pull of a magnet. Turns out, they're just two sides of the same coin. And this is the story of how one little accident started to connect the dots and, well, changed physics forever.
So, meet the guy who kicked this whole thing off, a Danish physicist named Hans Christian Ørsted. Picture this. It's the summer of 1820, and he's in the middle of a pretty standard university lecture. He's got a wire set up to show how electric currents create heat, and just kind of sitting nearby, he has a regular old magnetic compass. What happened next was complete chance.
I mean, you have to understand, the thinking for literally millennia was crystal clear. Electricity was one thing, magnetism was something else entirely. They played by different rules, they had different laws, there was absolutely no reason to believe they were connected in any way.
But then, right as Ørsted passed a current through that wire, he saw something that shouldn't have been possible. The needle on that compass, which, should have been pointing north, it twitched. It actually moved. He turned the current off, it swung right back. He turns it on again, and there it goes again. And in that one moment, a wall in physics that had stood for 2,000 years just started to crumble.
Ørsted had just stumbled onto one of the most basic truths of our universe. That little twitching compass needle could only mean one thing. The electric current flowing in that wire was creating its very own magnetic field.
So here's the absolute key. It wasn't just electricity, it was moving electricity. A charge just sitting there doesn't do anything magnetically. But a flow of charges, what we call a current, that's what does the trick. That one simple observation set off this massive chain reaction of experiments all over Europe, and it was the first real step toward uniting these two incredible forces. But here's the thing, this is a two-way street. If moving charges can make a magnetic field, it also works the other way around. An existing magnetic field can affect a moving charge. It gives it this invisible push. But this push works in a really, really weird way.
And in this whole interaction is perfectly summed up in what we call the Lorentz force. Now I know this equation from H.A. Lorentz looks a little intense, but all it's really doing is adding up the force from an electric field and the force from a magnetic field. We're going to zoom in on that second part, the magnetic one. That V cross B is just a fancy math way of saying the force is always at a right angle. It's always perpendicular to both the way the particle is moving and the magnetic field itself.
And right here you can see just how different these two forces are. An electric field, it'll push on any charge whether it's moving or not, and it pushes it straight along the field lines. But a magnetic field is pickier. It only pushes on charges that are already moving, and it doesn't push them forward or backward. It pushes them sideways. This is super important because it means a magnetic field can only ever change a particle's direction. It can never actually speed it up or slow it down.
And yep, this is the man we have to thank for wrapping all of that up into one beautiful equation. Hendrik Lorentz took decades of experimental data and synthesized it into this fundamental law of nature. It was work that eventually helped him snag a Nobel Prize. Okay, so a magnetic field can push on one single little moving charge. But what happens when you have billions upon billions of them all moving together? Well, that's just an electric current, right? And this force scales up from a single particle to an entire wire full of current.
When we talk about an electric current, all we're really saying is that there's this huge organized flow of charged particles. It's like a river of electrons flowing through a wire. And if a magnetic field puts a little push on every single one of those electrons, the combined effect is going to be one big push on the wire itself. And the great news is, we don't have to add up the force on every single electron. When they all flow together in a wire, all those little individual sideways pushes just combine. And the total force on that wire comes down to three simple things: how much current is flowing, how long the wire is, and how strong the magnetic field is.
And check this out. This shows you just how powerful that force can be. This isn't some special effect. If you get the conditions just right, in this case, it's a 1.5 meter wire that weighs 200 grams, carrying 2 amps of current inside a 0.65 Tesla field. The magnetic force pushing up can perfectly balance the force of gravity pulling down. The result? The wire just levitates. It floats right there in midair.
All right, so we've established that moving charges create magnetic fields, and that those fields then exert forces. But how do we figure out the strength and direction of the field that a current creates to begin with? We need a recipe for it.
So this is the big question that physicists were racing to answer after Ørsted's discovery. What's the exact mathematical connection between a current and the magnetic field it spits out? Well, the answer is
a thing called the Biot-Savart law. It sounds complicated, but it's a super important piece of the puzzle that lets us calculate the magnetic field from pretty much any electric current you can think of. It tells us exactly how much field is made by one tiny little segment of a wire.
Let's just break this down real quick. The law works by looking at one teensy little piece of the wire at a time, what we call the current element IDL. It tells us how to calculate the tiny bit of magnetic field, dB, that this one little piece creates at some point P, which is a distance r away. If you want to find the total field, you just do that for every piece of the wire and add them all up.
And really, that whole complicated-looking law just boils down to these 4 basic ideas. More current means a stronger field. Simple enough. The field gets weaker as you get farther away from the wire. It follows that classic inverse square law, just like gravity. And what's really fascinating is that the angle totally matters. The field is at its absolute strongest if you're looking at the wire from the side at 90 degrees, and it drops to literally 0 if you're looking straight down the barrel of the current.
So, we started this whole thing with an accident. A little twitch of a compass needle that connected 2 forces we thought were separate. But let me tell you, the rabbit hole goes way, way deeper. The work that came next, from James Clerk Maxwell, uncovered a connection so deep it completely changed how we see reality itself.
Just look at this equation. On the right side, you've got 2 numbers that are fundamental to our universe. That mu0, mu0, is the magnetic constant. It basically says how easily a magnetic field can form in a vacuum. And epsilon0, epsilon0, is the electric constant. It does the same job for electric fields. And when you multiply them together and take the reciprocal, you get the speed of light squared. And this is where Maxwell had this just mind-blowing realization. That equation was no coincidence. It meant that light is an electromagnetic wave. It's a wave of electric and magnetic fields, all intertwined and traveling through space. So electricity and magnetism aren't just related, they are the same thing. There are 2 aspects of a single unified force we call electromagnetism, and light is its messenger.
Which leaves us with one last, really cool question. We know from Oersted that a changing electric field, in other words, a current, creates a magnetic field. So does it work the other way around? Does the symmetry hold? Could a changing magnetic field create an electric field, and maybe even an electric current? The answer to that question would quite literally electrify the world.